by accident. They were skimming through. Thank you, Dan. Missed that. Just realized that, yes, I will go back and re-record that intro at some point. So yeah, someone accidentally missing one question. This doesn't introduce any bias, so we don't really need to worry about that one. We could deal with that missing data and it won't really cause any problems. Missing at random is a little bit different. It's where the data is missing and we can relate it to something that we've recorded in our data set. We can kind of draw a pattern between one of our columns and another, and the column that's got the missing data in it. And it can be something that can cause problems if we don't handle it properly. So for example, maybe we have patients in a trial and some of them are more likely to miss follow-up appointments. So we don't have that kind of subsequent data about them. But actually we know the patient's postcode, we know how far they were from the clinic, and we can work out that actually it's the patients that were further away that didn't have those follow-up appointments. And to be honest, the follow-up, the distance they live from the trial doesn't actually relate in this case to the severity of their disease. So it's not going to cause a big problem. So it's a little bit different to missing completely at random, but we do have some understanding of it. Now, missing not at random is the kind of problematic one. This is where the data is missing and it's the likelihood of it being missing relates to data we don't have recorded. So for example, you might have people in a minority ethnic group just being less likely to fill in the minority ethnic column. They potentially not wanting to record that. Or people with very high or very low incomes, if being asked about their income in a survey, deciding to not record that for reasons of social concern. This can be a real problem. This is an issue with our data set that we can't necessarily correct. So that's why it's important to try and understand what is going on with your data, to explore your data sets, to visualize the columns, to look at relationships, to look at where that data is missing and start to understand. Instead, just filling in the missing data there, kind of going through and going, oh, let's put the most common data, label in that ethnicity column, or is that, for example, is not going to actually produce you a good model. So as I say, missing completely at random is probably the best case scenario. So as I say, good to understand the pattern first, but when you have methods like, say, logistic regression or k-nearest neighbors that can't cope with missing data, or you've got instances where you want to have some level of control over missing data ourselves, you have some different imputation techniques and different ways of going through and putting in a value into that column, into that missing data that will allow us to proceed with our machine learning. So we're going to cover today mean imputation, median imputation, mode imputation, and iterative imputation. There are other things out there like k-nearest neighbors imputation. These aren't the only options available to you, but they're a nice starting point. So let's imagine that we've got a data set with an age column that looks like this. We've got a series of ages and we've got a couple of missing ages. And we're happy that we've looked through this and we think it's just, completely random. It's not a problem. So in this instance, let's go through and replace each missing value with the mean. We're just going to look at the column of data. We're going to add up all of the values that we do have, divide by the total number of values we have, and into our missing spaces, we put the mean, 26.9. Another option is the median average. So that's the one where we put all the values in order. We look at the middle, and in this case, the middle lies between 13 and 14. So we take the average of those two. So our median average is 13.5 for this data set. Finally, we've got the mode, the most common value in the data set. So you can see that we've got 3 12s, and therefore we're just going to say that the mode average is 12. Now, what you can also see here is that we've got some quite different variables. We've got some quite different outputs here. The mean and the median and the mode are not equal. That can relate to the shape of your data, the distribution of your data. Is your data sort of fairly central, or is it heavily skewed to one way? That might affect which of these you choose to use. Good news is it's actually really nice and simple to do within sklearn. sklearn provides the SimpleImputer. We can import this from sklearn-impute. We then set up the imputer. We identify what values should be considered as missing. So here we've said anything that's kind of classed as not a number we want to count that as missing. We don't want to count zeros as missing in this case. Maybe in this case, age, we do have some, under 1 year olds, so 0 doesn't mean missing. Other data sets, you might find that it's, a missing value is actually coded as 999 or the string missing. So you want to be able to control what it counts as a missing value. And then the great news is if you want to use mean, median, or mode, which is actually kind of called most common in this case, we just change the strategy parameter. So we've created this SimpleImputer, and then we apply this to our data set with the fit transform function. So we pass in our X training data set, and we use our imputed mean, we say fit transform, and we say, give me this output. The slightly annoying thing is this returns an array instead of a data frame. If you want to get this back into a data frame, we can take a copy of our original data frame. It's, you could just overwrite the original, but it's quite nice to keep a clean copy of our data set that hasn't had the values imputed so that we can keep track of that. But also then we just overwrite the values in this copied data set. So we've got a clean copy of the data set with a different name. Remember, we need to use the copy, otherwise it will be linked sort of behind the scenes and you'll start getting some really weird behavior. But we've done our SimpleImputer, we've fit transformed, and now we've got imputed values available. So we may want to further process this. For example, here the age is 28.99313. That's not really an age that's similar to the rest of our data, so maybe we want to round it. Simple imputation might not always be the best option. You might end up with a really big spike of values, which really radically changes your distribution. So here we had quite a lot of missing ages. We've got the original distribution from our age column over here on the left. Look at this compared to our mean imputed data. We've got this huge spike now. And it can also just lead to really weird, unrealistic values. So for example, you might have someone who's got a missing age and is also marked as a smoker. And then you replace it with the mode average in our previous example, and suddenly you've got a child being marked as a smoker. So one alternative to deal with this is using what's called iterative imputation. In this, you have a data frame with missing values. You fill in these missing values with, to begin with, a simple guess. So in this case, we've taken the mean average, but it could be something else. It could be the median, it could be the mode. We then build a regression model, or we don't build, sklearn builds for us, a regression model per column. So a machine learning model per column, a statistical model per column, however you want to think about it, to try to predict the values that we're missing. So for example, let's try and predict this column here, this 3153. We're trying to work out what values of A, B, and C. I've simplified this slightly just for the purposes of the example, but what values of A, B, and C minimize the error for predicting these values? What we're going to go through then is use the model. We've created a model where it's worked out these parameters to minimize the error across all of these different predictions. So we need the same value of A, B, and C for each of these. It will be used for this column. It'll have a different model for this column, different model for this column, but it's all the same model for one single column. We'll use the models to predict the missing values. So you can see our missing values have now updated slightly. We've gone through and predicted them, and there will be a little bit of error because it's a little bit difficult to, or potentially impossible to find values that work perfectly for every single, to predict every value in that column. So it will change slightly. And then we just keep repeating and repeating. So you can see we've built a new model, we've predicted again, we've built a new model, we've predicted again. Now we keep going until either the values stop changing between rounds or the maximum number of rounds is reached. But what this means is with this row being one person, this row being another person, this row being another person, that the values we are predicting are related to that person's data. It's not just sort of plucking the number out of thin air in the way that we're doing with mean or median, and it can give us a better final outcome. And compared to the mean imputation, in this case, we can see there's a lot less of a spike of a particular value in our data set. So this is the age column for our Titanic data set. We're showing the distributions here, most people between sort of 20 and 40. When we had this mean imputation, we had this huge spike, loads of people with an age now of about 28. Iterative imputation, it's not quite as good, but actually most people are ending up, it looks a little bit more similar. If we overlay the original distribution in red here with the new distribution in blue, you can see that we do have something that more closely approximates the original distribution, and it's a good place to start. Now, IterativeImputer is also quite nice and simple to apply, with the exception that because it's still classed as experimental in sklearn, we have to run an extra line first. So we need to run from sklearn.experimental, import, enable IterativeImputer. We then import the IterativeImputer itself. So previously we imported the SimpleImputer when we were using mean, median, or mode. Now we're going to import the IterativeImputer. Now, it was really annoying in the past to have to manually copy the data frame each time. So let's just make a function that will do it all in one step for us. So I'm going to create a function. I'm defining the function myself, and I can just reuse this every time I want to use the IterativeImputer on any data set. I'm going to impute the missing data frame. So I'm calling it impute missing data frame iterative. I'm going to pass in a data frame, and I'm going to pass in this special parameter called quarks. I'll tell you what that is in a second. For now, just know that it takes our data frame and it makes a copy of it, as we were doing before, and does imputed data frame. It creates a new variable called imputed data frame. In the imputed data frame variable, it overwrites the values of that data frame. So remember, we had this array that spat out. So we're just going to overwrite all of the values in the data frame with that array. We're basically just putting in our new values. Now, what we've got is our IterativeImputer, and we're using this fit transform thing again on our data frame. So we're passing in the data frame and saying, please use the IterativeImputer on it. And please take in these quarks, this quarks parameter. So it's keyword arguments, that's what that stands for. And we're using it to pass in any number of arguments directly through to the IterativeImputer. This is a really handy thing to be able to use in your own functions if you want to be able to pass something through. So rather than knowing, for example, in IterativeImputer, maybe we want to change the number of times it will keep going, going through and repeating those imputation steps. Rather than having to look up what that parameter is, write that into our own functions arguments, pass that over there, set a default, etc., etc. We don't have to do that anymore. We just know that anything that the user passes in as an additional argument when they run impute missing data frame iterative will just go straight to IterativeImputer and be processed appropriately. So you will find this handy, not just in this function. It's a useful thing to know about. So for example, here, I've run this and I've passed in what the minimum value should be. I've passed in what it should consider as a missing value. I've passed in what the random state should be. And I've not had to specify all of those in my function. I'm just able to pass them. It goes straight into IterativeImputer. And now we don't have anyone with an age lower than 0, which we could have had due to the way that these models get trained. But we know that wouldn't be realistic. So we've got no ages lower than 0. It's only treated not a numbers as missing values. And we've set a random state because there's an element of randomness in this with potentially what it gets initialized as, for example. So the random state parameter makes sure that we don't have that randomness. And actually looking at these as well, these two values have been imputed. With the mean imputer, they were both somewhere around 27, 28, and you can see with the IterativeImputer, we've got something really different. So simple imputation could be sufficient if your missing values are just missing completely at random. Multiple imputation might be a better option if your data is missing at random. Imputation generally can't really help if the data is missing not at random. You'll either just need to be really careful about the conclusions you draw. You'll need to really make sure you're communicating what the issues might be with your model and your data set. Now, for today's exercise, don't worry about which one to use. You won't have time to sort of investigate those patterns. Just, use whichever one you want to try out. But this is just important to keep in mind for your project, and also just for your general treatment of missing data in any analysis you undertake. It's not specific just to machine learning. For those of you who've done, sort of studies and stats modules, you'll have probably come across all this before. I won't go through these now, but just for reference, after the session, there is code for one-hot encoding and dealing with dichotomous columns in there as well. Now, feature selection. A few of you have started talking about this when we looked at feature importance in previous sessions, so well done for picking up on that. Feature importance is one of the things we can use to select which features we should keep in our model. There's a couple of different options. But basically, why do we want to do it? Well, feature selection, removing some of the features we have available when we're actually fitting our model, can make our model easier to interpret and explain. If we've got loads of columns and most of them aren't really doing anything, it can make it a lot faster to fit our model, a lot more computationally efficient. And it can also actually make our model perform better. We're removing some of the noise, some of the things that don't really matter. The model does try to automatically kind of not pay too much attention to those, but actually just removing them entirely can actually make your model better instead. Having too many features will generally start to degrade the performance of your model. Up to a point, it does help. As the number of features increases, the model performance generally gets better and better, but there will be a point that's sort of roughly optimal, and then eventually the performance may start to degrade. It may not happen within the number of features you have in your data set. It might be that you don't have that many, but in very big data sets with huge numbers of columns, it can be a real problem. We're going to look at a couple of different methods for feature selection. We're going to look at something called univariate statistical selection. We're going to mainly focus on importance-based selection and forward and backward selection. Univariate feature selection just involves looking at the correlation, the sort of, the pattern between each feature and the variable that we're trying to predict, the target variable. So we're just looking that, as the target variable increases, let's imagine we've got length of stay and we've got age. As age increases, does length of stay generally increase? Does it generally decrease? Is there no real relationship? Is it a really strong relationship, or is actually it might be there's some sort of link, but it's a little bit. So we can quantify the correlation. We can quantify this as a number. How strongly related are these features? Now, this is a really fast and simple way to do feature selection. Just keep the ones that actually seem to have a really strong relationship, but it can have quite a few big disadvantages. It means you can remove features which are not strongly predictive when you view them alone, but actually when you combine them together, they could be really important. And when you have lots of features that are correlated together, so it might not just be related to the target thing, but maybe age is also related to, the size of your ears, because your ears keep growing. So actually the size of your ears is also predictive, but only because it's strongly correlated to age, which is actually predictive of length of stay, for example. So the highly correlated features may all be kept in when, to be honest, just age would have been sufficient. So we won't go through this today, but you can read a little bit more in the links if you're interested in finding out more. Instead, we're going to look at a couple of different options. As I say, forward feature selection is the one we're going to start with. This involves incrementally adding features to the model. We prioritize the features that have the most impact on the model performance. So we just keep in the features that are really going to affect our accuracy, our area under the curve, our precision. We can choose which one it's scoring on, but we are going to prioritize the features that have the biggest impact. So in forward feature selection, you start out by training a model that's using one feature and one feature only. So maybe we have got our Titanic data set, and we're going to start off by training to predict whether people survive or don't survive based on their age. And we score that. And then we go on and we predict it based on their passenger class, and we score that. And we go on and predict it on, their fare, how much they paid, and we score that, and so on, until we have tried every single feature. And at this point, we then look at which feature did have the best performance, the most predictive power, and then we carry on and we add in one additional feature. So we've got, let's say it turned out that being male was the most strongly predictive feature for whether you survived or didn't survive on the Titanic. We're now going to go through and go male plus age. Let's score that. We're going to do male plus fare, male plus whether you're traveling with siblings or spouses, so on and so forth. And we're just going to keep doing that for as many features as we want to. Maybe we specify that we want to keep 5 features. Maybe we want to specify that we keep 8 features. Maybe we want the forward feature selection to work out how many features is the optimal for us. But we just keep iteratively going through and doing that. Backward feature selection is another alternative. It just is the same thing in reverse. You start off with every feature in your model, but you then take out one, and you take out one at a time. So we've got every feature in our model except age. We've got every feature in our model except fare, and so on and so forth. And again, we score them, see how well they perform, and we repeat until we've tried every single possible feature. We're then going to train this using features. We're going to remove one additional feature. So this time we've got rid of, let's say we decided fair actually didn't really do anything for the model. So we've removed fair. Now we're going to try and train it again, missing fair, and let's also take out age. Let's also take out, number of siblings and spouses, and so on and so forth. And we just keep iterating through, keep going until we've tried every possible combination, until we reach the number of features that we've specified or the optimal number of features as the backward feature selection algorithm has calculated. So the code for this, we import the SequentialFeatureSelector from sklearn. We set up our model. We don't fit it, but we set it up. So here I've created an XGBoost classifier. I could use random forest. I could use anything. It's completely model agnostic. I then create a variable for my sequential feature selector. I pass in my model. So here it's my XGBoost classifier. I pass in how many features I want to select. Now here I said 3, but I could also pass in auto as a string. And then we specify the direction. Do we want to do forward feature selection? Do we want to do backward feature selection? We fit the feature selector on your data, and this can take quite a few minutes to run, potentially hours if you've got loads of data and you've specified, depending on, if you're working forwards and you've said you want to, you want to keep 30 features, that's a lot of things for it to potentially evaluate, especially if you've got, 150 columns. So it can take a while. Then what we're going to do is we're going to grab a list of the names of all of our features so that we've got these. So these are the original features in our data set. We're then going to mask the feature names. So we're going to turn our feature names. So this is just a list of, age, sibling, age, fair, is male, whatever, as strings. It's just the names of our columns. And we're going to use the SFS, remember we created this variable, SFS forward. It's a sequential feature selector of doing forward selection. We fitted it to our model, to our training data set, and we're going to use this getSupport method. Now, getSupport returns a list of true and false. So if the sequential feature selector decided that this feature actually did have suitable predictive error, that it was worth keeping in the model, then it will return true. If it wasn't worth keeping in, it will return false. By applying this to our feature names, what we get is just a list of the features that the algorithm has said we should keep. So we've got those features now that we can refer back to. If we then fit a model just using those features, so we've got our training data set and we've said, please just keep these features, then we can take the output of the feature selection forward and use it later on in our model for any training, any prediction, and so on and so forth. As I say, it can be really slow depending on how many features you select. And it's also worth noting that forward feature selection and backward feature selection, if you specify 5 features for both, they may not produce the same results. Other parameters can also influence the best combination of features. So when you're hyperparameter tuning, you may find that different combinations of features are actually the most important. So this isn't something that can necessarily be done entirely in isolation from all the other steps in your process. But it's fine to start with it as that, get a good model tuned up and then try playing around with feature selection. Different models may not all benefit from the same features being selected as well. So a logistic regression, for example, could require and benefit from a different combination of features to an XGBoost model. So again, if you change out the model type that you're using, you may need to rerun your feature selection. Now, in the session on explainable AI, and also a little bit throughout as well, we've been looking at some of the different ways of exploring feature importance. So we've got logistic regression coefficients. We've got mean decrease in impurity for tree-based models. We've got permutation feature importance as well. Now, if a fitted model has a built-in attribute called feature importances, which a lot of these models do, logistic regression has them, decision trees, random forest, XGBoost, these all have a built-in feature called feature importance, a built-in attribute called feature importance. We can make use of that, sklearn can make use of that to help select features. So for tree-based models, it will be the mean decrease in impurity. For logistical and linear regression models, it will be the model coefficients, and so on. This time, we import SelectFromModel instead of feature selection. Instead of sequential feature selector. We still create our model. We ask it to select from model. We pass in our model and we set a threshold. So this threshold is just a value. So when you've got your mean decrease in impurity, when you've got your coefficients, they will all be numeric values. And we're just setting a threshold that we want to cut it off on. You may want to look first at what your values are to actually get a sense of how those are distributed rather than just setting the threshold, or you can pass in automatic again. Then everything else is basically the same. We get support, which is that true, false. We apply that to our feature names and we work out which features it has decided are important enough, which meet our feature importance threshold that we should keep in. So which should you use? Well, forward and backward selection, as I say, do tend to find similar lists, but they may differ slightly. You could potentially run both and combine the output so it keeps all of the, the sort of union of both of those. So you're not potentially missing out something that is valuable. And the feature importance methods are really good, but do be aware of some of the limitations of coefficients and mean decrease in impurity that were talked about in the explainable AI session. You can go back and have a look at those if you're concerned. You could also manually get a list of feature importances using permutation feature importance, which does overcome some of the issues of things like mean decrease in impurity. And then you can use your own threshold to determine which features to keep. So that's another option. A thing we won't talk about today is dimensionality reduction. So let's imagine we've got a data set with 500, 600 columns, really big data set, it's collected from wearables or something like that. We might want to use something called dimensionality reduction to capture the details of all of these columns in a single or much fewer columns of values. We're not going to actually go into these methods because it's really complex, but if you want to go away and have a look into this, the most famous one is probably principal component analysis. In the domains you're working in, the problem with dimensionality reduction is it generally makes things less interpretable. Your columns, like age and fair don't exist anymore. They've been sort of amalgamated into a single column, a sort of single super column potentially. So feature selection is probably generally the better approach. It will make your model more interpretable rather than less interpretable. And most of the time that's more important in the kind of models you'll be building rather than the raw performance gains. But it's just useful to know it exists because you will probably come across it in your quest to try and reduce the number of features you have. Right, next one, feature engineering. While we want to avoid having unnecessary features in our data set, a really crucial part of the setup stages can be something called feature engineering. In our Titanic dataset, we could use all of our data manipulation skills to add some extra columns, and these extra columns could actually have really good predictive power. So, for example, we've got the cabin number of people. Well, actually, the first bit of the cabin number is the deck they were on, and that might be easier for the model to predict on than just the cabin number string. We could work out the total number of people they were traveling with rather than just having it split across several columns. We could have an adjusted fare. So for example, the fare was the total fare for everyone traveling on the same ticket. We can work out how many people did travel per ticket and then adjust the fare to give a better indication of the actual fare people provided rather than incorrectly suggesting that some people had an incredibly high fare, which might have suggested they were in a very high-end column, when in fact it was just 8 people traveling on the same ticket. We could create a binary column, a binary flag for whether they were traveling alone. We could create some sort of feature from their names to work out whether they were nobility or kind of titled in some way or something else about their class. There's no single way to make each of these. You will gradually find different ways within your pandas manipulation to create different kinds of data. But I'm just going to give you a couple of examples today to give you a few ideas that you can start to reuse for your own data sets. So simple string extraction is a great place to start. In our data, each cabin number is a string of data like this. So C85, E46, for example. The deck in this case is always the first letter. So we can just say, please take the cabin and take the first letter of the string, which we use with this .str0. We're saying the 0th position. Remember, Python counts from 0, and this extracts the deck. So we've got C here, where we didn't have a cabin number. It's just coped with that fine and left it as not a number. And then we've got missing that, and then it's dealt with the E here. We have values for siblings and spouses as well, parents and children. It can be really helpful to have a total sum of the number of people someone's traveling with. So we can add together two integer or float columns just to create a new column. We specify the name of the new column. That's not something that already exists in our data frame. We're saying, please create this new column for me, and it needs to be the sum of these two. It's possible that people traveled in other groups. Maybe they traveled in as a group of friends or a group of people working together, and our parents and children or our siblings and spouses columns aren't going to pick that up. So what we can do is we create a data frame of people the number of people who traveled on the same ticket. So what we've said is, please count up the number of times that each ticket appears in our data set. We've reset the index in this case because we don't want the ticket number to be the row names. We want it actually as a column. And we're going to rename this, this column here, which came out as ticket, to the number of people that the ticket was shared between, just because it's easier when we then join it up with our main data set to see what's going on. We're then going to merge this with our original data set. So we've got our original data frame, we've got the count data frame that we've created here. We're going to tell it what we need to join on. What are the common columns between the two? In this case, it is the ticket number. And we're going to say that we want to keep all of the original rows in our data set. And then we're going to get rid of the extra column. We don't need this index column anymore. It's surplus to requirements. All this means, don't worry too much about the details, but basically, if you've got something that you want to create a count up of, and this can be really useful, say if you want to calculate percentages of a total within a group, something like that, that you can then start to build up these more complex data frames. We can do other operations at that point, so we can subtract, divide, multiply. We could get the remainder with modulus. If we've got float and integer columns, these will just work. So here we've now got the number of people that were sharing a ticket, and we can calculate a fare per person by dividing the fare column by the number of people that the ticket was shared between. We can also create something like a binary flag from other columns. So here we've got values for siblings and spouses. We've got values for whether people are traveling with parents and children. Maybe we just want a simple binary column to say, actually, someone had neither of these with them. So we're going to create a new column called traveling with family. And we're basically going to create an if statement. We use the npwhere function for this. And we say, please add up the number of siblings and spouses, the number of parents and children, and check whether it's greater than or equal to 1. If it is greater than or equal to 1, please put a 1 in the column, which, so they are traveling with family. If it isn't greater than or equal to 1, put a 0 in the column. And this is a really handy pattern for simple conditions like this. And if you've used an if function in Excel, it'll probably feel quite familiar. I'm not going to go through this now, but we can also start to extract really complex things from strings and start to build up really advanced conditions that are checking multiple things at once. But do have a look at these slides if you're interested in that, but I don't think it's worth spending the time on right now. So in your own data sets, you may find other features you can engineer based on your domain knowledge, or there's additional data you can bring in and join up. Instead of having a column of patient postcodes and clinic postcodes, maybe you could go away and use your skills from module 3 to calculate the travel time and use that as a feature instead. Maybe you can calculate additional metrics from columns you've already got. So if you've already got height and weight, maybe calculate body mass index, or maybe you can calculate frailty scores, risk scores from a series of measurements you've got. You could simplify multiple diagnosis codes into categories of disease. So, for example, instead of having, ICD-10 codes for different, autism, ADHD, etc., maybe you could just group that into a sort of neurodiversity flag. You could add in columns for time since last visit or last admission, last test. You could count things like the number of previous admissions in the last couple of months. You could split raw test results into something like abnormal or normal, or low, normal, and high. These are likely to give your model a lot more predictive power than just using raw data. And to be honest, the feature engineering is often the biggest thing. It's not necessarily getting more data. Well, it is often getting more data, and feature engineering will probably get you more gains in your model performance than all this hyperparameter optimization, etc. So this is a crucial part, and it's a part that takes time to build up because you're just learning to manipulate data in pandas. Great news is the more you manipulate data in pandas, the more you can use it for other things like your day-to-day analyses. It's something that is a very beneficial skill to build up. I've just covered a couple of the ways you can start to extract and create new columns today. There's loads more out there and nice different ways of doing it. So have a play around. Now, splitting your data set. We've talked previously about the need for splitting our data set into training and testing. So this is just a little bit of a recap. This ensures, I think you're all familiar by now, we can check how our model may perform on real world data. However, we've said a few times it's actually better to split this data further into 3 data sets. We've got our training data set, we've got our validation data set, which we're going to use when we're trying out different models and hyperparameters, and we're going to have our testing data set, which is what we're going to use to check the likely real world performance. And we keep that separate until the very end, until we've done all our hyperparameter optimization, all our feature selection, all our feature engineering, all the stuff we talk about today. This testing data set, you should not touch that until you're finished with your model effectively. Good thing is, this isn't complicated to achieve in code. So you just split twice. You create your training and validation set, and you create a testing data set using the train test split. Out of that, we get 4 variables. We got what I've called xtrain and val, xtest, ytrain and val, and ytest. I then just pass in this training and validation set, this big 80% over here. I pass it in again, and this time I split it into my xtrain and xvalidate, my ytrain and my yvalidate. And I've now got the different data sets that I can use, my training, my validation, and my testing. Stratified splits. So imagine you've got 1,000 positive cases where people survived, 50 were negative cases where they died. There's a possibility that at random, most of the died cases could just end up in your validation and test data, very few in your training data. Your model's probably not going to be able to learn the patterns, therefore. Stratified splitting ensures that the balance of classes stays the same when you split the data up. Now, the good news is you don't need to do anything. Data is stratified by default when you use the train test split function in sklearn. You don't need to go away and do anything yourself. Now, we can take this even further, and we can use k-fold validation. So we're going to here split our training and validation set into several parts. We're going to train the model that many times, and we're going to average any metric scores across all of those different runs. At the end, you train your final model on all of the training and validation data set, and you will use that on the test set you've held back after you've done all of your optimization, etc. So here we've done 3-fold validation, so k equals 3. We've used 2/3 of the data to train and 1/3 to test. We've then used that first third for training, the middle third for validating, the final third for test for training. And here we've used the first third for validating and the final 2/3 for training. So you're getting a better sense of the performance on different data sets, on different splits, on, it's a better way to get a good overall sense of how it will perform on real world data than just using a single train test validate split. It does make your code a little bit more complex, which is why we haven't generally used it for a lot of the examples, but it is good practice to use it in your own models. All we need to do there is to import cross-validate. So instead of from sklearn import train test split, we've imported cross-validate, we've created our model, we pass in our model and our training and validation data set. We tell it what we want to score on. So the nice thing about this actually is we can say, please score on multiple things at once. Score on the accuracy, tell me the F1 score, tell me the area under the curve. We can tell it to do all this fitting in parallel. So if we set the number of jobs to -1, it will try and use as many threads on your processor as it possibly can, rather than doing one training, training one and moving on to the next, and moving on to the next. It will try and do them all simultaneously. And here we said we want 5-fold validation. So previously in that example here, we had 3. Well, actually, let's split this data set up into 5ths instead. So we will end up with 5 lots of scores because we've trained and tested 5 times. And then we can start to look at how much the scores vary. If they vary a huge amount, then your model's not potentially very stable. It's quite dependent on how the splits have ended up being. If they're quite close, if there isn't a huge range in the testing and training, in the validation scores, then your model's a little bit more stable, a little bit more robust, slight tweaks in the training data. And we can still predict as well. After we've, we pass in our model, we pass in our training and our training data set, and we're predicting here the training the predictions for the training and validation data sets, or we could pass in our validation data set. So, imbalanced data. As I say, bit of a whistle-stop tour. You'll be pleased to know there's only 15 minutes left, and we're getting towards the end of this section. Imbalanced data sets, where you have lots of more of one class than the other, they're common in real-world classification problems. When you test people for a disease, only a few will probably have it. Out of a lot of interactions that happen, only a few may end up having adverse outcomes. So in the last session, we talked about SMOTE for creating additional synthetic data points. And this is one example of an oversampling technique. You could also do something called undersampling, so you could just get rid of some of your majority point classes. You can just chuck them out of your data set, not use them for training. So the imbalance isn't as bad. The easiest additional option that's available to us is built into models. Worth knowing about this. So quite a lot of the models we've covered have some sort of parameter to adjust the weighting given to the minority class. In logistic regression models, this is just called class weight, and we can pass in balanced. In XGBoost, we need to work out what's called the scale pos weight parameter, and it's a way to, again, adjust the XGBoost model for these imbalanced data sets. What we want is the inverse of the class distributions. All that means is how many people do we have in the negative class? So 0 didn't survive in this case. How many people do we have in the positive class? Did survive. So we just need to calculate how many survived, how many didn't survive, divide the number that didn't survive with the number that survived, and that's all we need to pass in. And it will help the model deal better with this imbalanced data set without having to resort to SMOTE. Like, again, this might not always actually improve it. So in this case, I was trying out XGBoost. We did find there was an improvement on the Titanic data set when we passed in this parameter. Logistic regression, the scores weren't actually as good, but it really helped to reduce the false negatives, but at the expense of increasing the false positives. So do try it with and without and see what matters for you in your data sets. And remember as well that when you're working with imbalanced data sets, it's just important to think about your metrics that you're using. So accuracy, as we've talked about a lot, can be misleading. There are other options like F1 score, precision, recall, balanced accuracy, etc. Right, last one I think we're going to get onto in the time available is hyperparameter tuning. So you've probably already tried to optimize parameters in your models. When you were working with random forest, for example, you could tune how deep the tree is, how complex it becomes, the total number of trees to train. Remember, random forest is lots of different trees all working together. You can work out which metric to use for calculating splits. You can work out the minimum number of samples that we require to split our data sets, the minimum number of samples required in each leaf. You might have started using a series of nested for loops to try and work this out. You'll be pleased to know there are some other better options. Grid search allows you to specify a series of parameters of interest, the range of values they can take, and it will try out every possible combination and return the best scoring combination for you. We import the grid search CV. We specify a list of parameters. Well, we specify a list that is a dictionary of parameters. So we pass in this case, the criterion, whether we're using Gini, entropy, or log loss to define our splits, if you cast your mind back. The maximum depth of the tree, we're saying that we want the maximum depth to be anywhere between 1 layer of detail and up to 15. Remember that the actual number we specify here doesn't get included when we use this range function. Minimum sample split, again, we want this to be anywhere between 2 and 15, and minimum samples leaf between 1 and 15. We pass in to the grid search CV our model that we want to look at. I've chosen decision tree here rather than a random forest, same parameters. I've passed in the parameter grid that I've created here. I've said I'm interested in scoring on the accuracy. I could say I'm interested in scoring on the receiver operating curve. I'm interested in scoring on the recall, anything that is the most important thing to me. And then I said I want to use this cross-validation that we just recapped. I want to do 5-fold cross-validation in this case. I'm going to fit this to my training data, and then I'm going to extract the best parameters, the best possible combination it found, the one that gave the highest score for accuracy. And I'm going to check the test set. So we can then do anything afterwards that we do with a normally fitted model, like score the outcomes. So that's all fine. Now it can start to take a really long time to do this. We've got 3 options for split, 15 options for max depth, so on. In this particular instance, we've got 9,450 combinations. We're evaluating them 5 times per model, and that's 47,250 model fits that our computer needs to do. We can try instead something called randomized grid search. Instead of trying every combination, it randomly selects a certain number of combinations to try. This can help you find perhaps a good enough combination of parameters. As I say, hyperparameter tuning is useful up to an extent, but it often isn't the best way to spend your time. It's a good way to spend your time, but you can spend an awful lot of time trying to tune hyperparameters to eke out a tiny improvement when actually spending some time on feature engineering could be better spent. It can also help you narrow down the ranges of hyperparameters that you want to tune in if you're using this randomized grid search, and then you can use the exhaustive grid search on this slightly smaller range of parameters. I won't go through the details here, but the code is very largely similar. There's just a slight change in the random number generator you need to use. Now, the Optuna framework is an open source framework for automating all of this away from you. It kind of works in a similar way, but it actually uses algorithms to give up on areas that aren't looking promising. It starts searching and goes, no, these are useless sets of parameters, this range of parameters. I'm going to focus in on this instead. Great news is it's actually framework agnostic to a certain extent as well. You could use it with deep learning models, not just your sklearn models. We import Optuna, and it also comes up with a nice range of plots for us as well. So we're going to import those plots too. We're also going to import the cross-validation score from sklearn, which is going to help us to score the performance of the different models that Optuna comes up with. This looks scary, but it's actually very similar. We need to define a function called objective, and we pass in a parameter called trial. Now, all we need to do, this is very similar to what we were doing a minute ago. Remember, we had criterion, Gini, entropy, log loss. We had max depth, 1, in this case, I've gone up to 32, minimum samples, leaf, etc. Now, all we're doing is saying, please suggest a categorical variable, select a categorical variable from one of these for the criterion parameter. Please suggest an integer from this range for the max depth parameter, and so on and so forth. We create our model within this function. We pass in the random forest criterion. So here with the variable we created, we're passing that in to the criterion. So is it Gini? Is it entropy? Is it log loss? We're passing in this variable to the maximum depth parameter in the decision tree that we've created, and so on and so forth. We then need to effectively return a score. That's what the model is expecting us to return. So we're going to ask it to return the cross-validation score. We pass in the model. We pass in our training and testing data set. In this case, I'm going to do 3-fold cross-validation, and we're going to take the average of those for our final output. So it's just basically trying out one of these values in the model, scoring it, and returning the accuracy. And it will do this again and again and again, gradually narrowing down the best combinations of parameters to use. For Optuna, when we create the study, in this case, we say we want to maximize the accuracy. We run the optimization, we pass in our objective function that we've just defined, and we tell it we want to do a maximum of 1,000 different combinations. We get the best model from the run, and we print out the accuracy and the best hyperparameters. So it's nice and simple, a nice, efficient way to get a really good set of parameters. And we can also use some of these plots to look at things like how the accuracy improved as it tried different combinations of parameters. You can see here, even with the first combination of parameters it tried, that it got about 0.805, maybe a little bit above that. It never really got much higher. So this red line shows the improvement in accuracy, our objective value, what we were trying to maximize over time. It never really got much better. And the lowest it ever really got was 0.77. So the hyperparameters made a difference, but they didn't make an absolute world of difference. And you can see that after about trial 100, we didn't get any further improvement. And there were lots of combinations of hyperparameters that did produce the same objective value. We can also look at the importance of the parameters with this, and we can look at the a more complex plot for starting to understand how variations in different features, linked up with each other. But don't worry too much about these. They're just there if you're interested in poking around. There's also the Optuna dashboard. We won't cover that today, but if you're interested, take a look. It's a nice interactive way of looking at your optimization in more detail. And as I say, bigger gains can often be found from more data, better data, feature engineering. So just consider whether feature engineering is the best way to spend your time. I will quickly cover ensemble models and then we'll stop. One nice little way to try out getting better performance of your models is to use ensemble. All it means is in some way we are combining the output of multiple models. This can give us models that perform better, they overfit less, and they're more robust. Now, we can create models using a voting classifier. So here, let's say I trained 5 models, a logistic regression, a k-nearest neighbors model, a random forest model, an XGBoost, and a light GBM. And in this case, 4 of them predicted that the person on the Titanic died, 1 of them predicted it survived, and we will take the majority class. This is called hard voting. It takes the majority class out of all of those. We can also do soft voting, which looks at the predicted probabilities of each output and takes a final averaged prediction to produce the final output. Now, this is nice and simple to implement. The code is there if you want to try it out today as well. But basically, the benefit of these ensemble models is that it makes them less likely to be strongly affected by the quirks of a given model. You're sort of accounting for the strengths and weaknesses of different kind of models by combining the outputs together. And you can start to also get a sense of how variable the model predictions are by looking at, did 4 out of 5 agree? Did 5 out of 5 agree? Or actually, was it a bit more split across the different models that you've created? So I'm going to stop there. There's a couple of additional things that you might be interested in looking at, and I'll create some additional videos for YouTube on these things that we didn't have time for today, but I'm conscious that I want to give you time to play around with a new dataset. Pipelines are just a nice way to simplify your code with sklearn. There are auto machine learning libraries that will automatically suggest a good model and set of hyperparameters for you, but they don't always do that well. So it's useful to know that they exist, but might not be the best option for you. And calibration is just making sure that when a model outputs a probability of something like survival or how likely it is someone that has a disease, that those probabilities are actually meaning what you think they mean. Quite often they don't, and you may want to assess if the probabilities are important to you, whether the probabilities truly reflect reality. And there's a little bit about how you can deal with that if you need to as well. So I'm going to stop there and go on to today's exercise. Dan, were there any questions?
Yes, about 10 million.
Fantastic. Good to hear.
I'll flag up a few. You might want to trawl back through the chat. I've tried my best to answer things. Other people have been far more helpful than I have. And some of them have been answered. But there are a few that I flagged up. One said, is it possible to estimate the maximum predictive accuracy of our dataset for our output? There must be a mathematical representation of the amount of information available on a dataset. If not, how do we know when our model is as good as it can be? So I've kind of answered, well, typically we measure potential performance via ROC curves. That's our good metric for that. But I didn't know if you had any thought. I'm not a statistician, so I don't know if there's a more statistical way you could explore that. So I didn't know if you had any thoughts.
It's a good question. It's not one I also immediately have an answer to. I think my sense on a simplistic level would probably actually be just, I think a lot of these more modern fee-based methods that we've talked about just probably do get the best performance out that you can get fairly quickly. So you, at that point, only a little bit tweak, you're only going to get, as I say, sort of fairly incremental, slight improvements with all this hyperparameter optimization, etc. So I would almost use that as my benchmark of, has this got, how much predictive power does this have? Is that if the gold standard machine learning models are not producing a good output, then it probably doesn't have very good predictive power, and you need to go back to the data set and find more data, feature engineer, etc. But there may well be a more sort of robust statistical way of doing that, but not one that I'm aware of.
Yeah, thank you. So there's also a question about the threshold. So on slide 39, you set the threshold to 0.03 when you're looking at your SelectFromModel package. And the question was, is that kind of a bit like the classification threshold where you have a kind of default? Is that a decent default, or is it just more specific to your particular data?
Yeah, in this case, it was model specific. It was just kind of cutting down to a smaller number of features. In this case, after looking at the feature importances, set the threshold at that. So I think, as I've seen, Yiwen has shared a really nice bit on selecting the feature threshold there. So I would always recommend probably just having a look at your feature thresholds, trying out some different thresholds as well, and seeing how that affects your performance. And I'd also echo what you said, that the sklearn documentation is actually really good. In addition to a lot of your data for your sort of standard, this is what this function does and this is all the parameters, there are a lot of guides that go into a bit more detail about either the theory or how to interpret the sort of different plots, the different metrics, etc. So it's definitely worth having a look around in there for anything that you're kind of wanting to know more about.
Awesome, thank you. So I think most of the other questions were largely answered. There was a question about whether you'd use, when you're looking at forward-backward selection, whether you'd use a sample of your training of your data set rather than I've kind of suggested you typically want to use your entire or the same data set that you are going to use for your training set in production. I don't know if you had any extra thoughts on that.
Yeah, I think I, again, not immediately got I have heard of people doing that, sort of reducing the number of possible features it can select from at each step, just to simplify that. Why does that feel familiar? I think that, yeah, I'll see if I can find that documentation for that, because I think that does, a lot of this time, as we say, we're not necessarily going to be able to achieve the best possible model ever, just due to the limitations, the computational limitations of trying to evaluate every parameter, but that will probably, again, find you a good enough outcome. So I think that's definitely a reasonable thing to do.
And the last thing, I'm going to be cheeky and I'm going to ask a question. It just struck me when you were looking at the grid search. I wonder if anybody's looked at using, it may not, you've got Optuna, which probably does the magic much better, but I wondered if anybody, just thinking about the reinforcement learning stuff we did last week, whether a kind of reinforcement learning approach as an optimizer, how well that might perform on something like this, where you've got a very large solution space. I don't know, it might be rubbish, but it might be quite interesting to try.
Yeah, again, not something I've seen, but I would also be interested to kind of hear if anyone's trying that out. Yeah, I think from experience and from what Mike in our sort of Pencor team, who does a lot of the machine learning work, has said, Optuna is just, a really good framework, does a really good job of finding those optimal hyperparameters. Worth noting as well that things like the sklearn pipelines, which I haven't gone into today, can also help you to optimize multiple hyperparameters at once. So not just the kind of parameters of your model, but actually things like, how can we combine the number of features we've selected and the imputation method with the final, the actual prediction, the model hyperparameters as well. So you may want to look into that as well, because as mentioned, they do all interact, and just looking at the model by itself sometimes might not be enough, but that does get a little bit more complex. Just another one to be aware of if you do go down the machine learning rabbit hole for your project.
Definitely. I think you've answered most of them, but thank you. Yeah, but if there's anything in the chat that jumps out, obviously just jump on it. But I think most people. There was an excellent discussion early on around missing data and the national data opt-out, and an excellent report that Don shared around that he'd written around that. So if people haven't seen that, he shared a link to that report. So do have a look at that, because it appears there are particular cohorts of people who are more likely to opt out, and that could be interesting and useful information if you are looking at using that kind of data for your machine learning models.
Yeah, absolutely. I think the other thing I'm seeing as well, I will be collating some of these resources into a document so that we've got all of them available. There's some really nice stuff here on end-to-end code, which I think is definitely something that would be useful to have. And hopefully that's sort of what you'll start to build up in your groups today, a nice reference individually for some end-to-end code. But the value of that, it's very useful to have. And the other thing, there's some discussion about deployment going on, I've just seen in the chat, and that's something, again, if we have time, I'd quite like to explore some masterclasses during phase 2 to help talk about deployment, to talk about things like APIs for accessing in new predictions, in production, and that sort of thing. So stay tuned, we may have some extra content around that area. Fantastic. Right, I am going to go on to the exercise. So in the exercise in your groups, you're going to have a chance to practice everything you've learned in this module, any bit that you're interested in. Doesn't have to be the stuff from today. I'd recommend you try a little bit of the stuff from today, because whilst we've covered a lot, but actually a lot of the time the code is only 2 or 3 lines for some of these things that we've talked about. So I've given you a series of possible data sets that you could work with. I've sort of lightly screened these to check that they look, they're not going to be too complex to work with. But, you might want to take a look at them. If you click into the links here, it takes you to some information about each data set. And also there are direct data set links that you can put straight into Pandas Read CSV, not Pandas Read Excel, that should just be Pandas Read CSV. And, you don't have to download the data set. You can just point it at this link and it will work straight away, which is useful if you're using Colab. But most of these, the first 1, 2, 3, 4, 5, 6 are classification data sets. The last 2 are regression data sets, predicting these numeric values. So if that's something that you think is more interesting to you, because we haven't done so much practice of that, then your group might want to try those out. Remember that you will be using different metrics for those. You might have to refer back to the end of module 4E's session for a little bit about those metrics. And also these classification data sets are a lot more similar to the stuff that you've been repetitively doing throughout the course. So that might feel easier to work with. In your data set, in your exercise, I just want you to try and train a model and provide some level of evidence that you've optimized your model in some manner and kind of checked how good your model is. After you get past the point of importing and maybe sort of prepping your data, training a first model, you may want to split your tasks up instead of all working together simultaneously. You may want to keep working together. That's absolutely fine. There's no right or wrong way to tackle this. Consider what to do about imbalanced classes. Consider things like SMOTE or what we've covered today. You can use any model we've covered. You could just stick with the logistic regression. You could try any of the boosted trees. You could always try a deep learning network. If that's something that you want to have a bit more practice with, consider doing that in your group instead. You could choose one algorithm. You could try a couple of different ones and compare the performance. At the end of tomorrow, I'd just like you to pop your notebooks into your groups, and I will award some ad hoc points to just good things that I see in notebook. I'm more interested in good comments and exploration. I'm not so interested in raw performance. I just want to see evidence of you trying things out. I'd like you to try and include at least 2 of the things we've covered today. So whether that's some feature selection, some imputation, some sort of grid search or hyperparameter tuning. We didn't get to these last few things, but they are in the slides if you want to have a poke around. So that would be ideal. Try and include a couple of them. But, you know, consider you could have one of you going off and doing some exploratory data analysis, looking at the distributions of different bits of data. One of you could be focusing on making sure you've got a nice wide range of model metrics and that you've created, say, confusion matrices, your ROC curves. Someone could be looking at explainable AI. Someone could be looking at model decisions, you know, feature importance, SHAP, etc. And you could even just be sitting there writing out, are there any ethical considerations with the data sets that you're looking at? Could you actually put this model into production if it was a real data set? Are there any other issues you've identified with the model? So just that, like I say, there isn't a right or wrong answer. I want you to treat this almost as though it's you know, you're starting your project and you want to try and train a machine learning model on a real data set and see if there's anything in it. Is, you know, as the question was, is there any predictive power in this data set? And just get used to starting from scratch. So you're going to take a 10-minute break now, and then you'll be in your PSGs until the end of the session. I won't bring you back before lunch. That's just going to be it for the end of the day, but I will be floating around. I will also share the links to all of those data sets in the class channel. But do shout if you kind of just get started and completely get stuck, don't really know where to begin, or if something doesn't seem to be working, and I'll come around and see what I can do. So any questions about that? I'm not seeing anything in the chat.
Just while I've got, sorry, Sammy, just while I've got people who obviously will be floating around, and we'll start this afternoon session at 1:30. But just to say that I'm still waiting for a couple of groups, just 2 groups left now. I think Sid and Paula. Can you, even if it's over lunch, just very quickly decide on your sarcastic reviews? Because I do need those for next week's session. So please, if you haven't submitted that, please do so. Thank you.
Right, I shall open up the breakout rooms and do take a break. And we'll see you after lunch. Thanks, everyone.